Chapter 2, Lesson 6 of Pre-Calculus, going to look at graphs of rational functions. We'll be taking a look at rational functions, what they are or what their characteristics are. We'll look at a specific rational function called the reciprocal function. We'll look at limit and asymptotes, and then we'll go ahead and graph those rational functions. Rational functions, to begin with, are functions where you have a polynomial in the numerator and a polynomial in the denominator. Now, because we're talking about expressions that are fractions, this denominator cannot be 0. So anything that would make this denominator or this polynomial function 0 in the denominator is going to create an asymptote. And that asymptote is going to be a vertical line. You should remember from last year that zeros of the denominator are x values that we can't use, so there are no y values at those corresponding x values, so those are vertical asymptotes at the zeros of the function. Now, we just spent 3 lessons on determining the zeros of these functions, so make sure you apply that and remember that when you're asked to find the zeros or the vertical asymptotes. In many cases, this polynomial function in the denominator will already be in factored form, so finding the zeros is rather easy. But if it's not in factored form, just make the connection. You need to find the zeros, and so you're going to have to apply those things we just learned in the previous lessons. So very quickly to summarize then, a rational function has a polynomial in the numerator and a polynomial in the denominator, and the domain is going to be any real number except those zeros of the denominator. All right, and most rational functions will look something like this. They will have a place where there's a vertical asymptote, an x value that can't be used, and because that particular x value can't use, there's usually a y value associated with it that can never be produced, and so you're going to create these horizontal asymptotes as well, or end behavior asymptote. This actually is a graph of the reciprocal function, which we'll take a look at in a little bit more detail in the next lesson. In the rest of this lesson, I want to talk about specifically using limit notation, and I want to use limit notation in the bottom part of this paragraph to describe a vertical asymptote. Now, we've used limit notation to describe the end behavior of the functions, the limit as you approach positive and negative infinity. Well, you can also look at the limit as you approach a particular value from the left, negative infinity, or from the right, positive infinity. And what this little paragraph down here says is that if you have a line x equal a, where a is just some real number, so some number along the x-axis, if that line at that value, that vertical line, is an asymptote, as you approach it from the left or the right, the y values are going to end up going towards either positive infinity or negative infinity on both sides of that line. Now, they can both be going towards positive infinity, they can both be going towards negative infinity, or one can be going to the positive, one can be going to the negative, but it doesn't matter. As you come close to that point, that x value from the left and from the right, the y values are going towards infinity on both sides. That's what in limit notation would describe a vertical asymptote. So what we want to practice then is using this limit notation that we have. Excuse me, I had a little lunch. What was I saying? Oh, we're going to use this limit notation down at in the denominator. I'm not worried about fractions. I'm thinking about that. All right, I'll get it out. We're going to use this limit notation to describe the graph as it approaches this vertical asymptote. And so the best way, I think, is to do an example or two. So let me go ahead and do that for you. So here we have these 3 functions. This is a rational function because we have a polynomial in the numerator, a constant, and we have a first-degree polynomial in the denominator, so it's a rational function. So to figure out what the asymptotes are, the vertical asymptotes, those are going to be the zeros of the denominator. So whatever makes this denominator 0, in this case negative 3, so x cannot be negative 3 because that would make my denominator 0. Therefore, I'm going to have an asymptote at the line x equals negative 3. So if I graph that, and I'll graph that on the calculator, you'll see, I'm going to use this little line right here as my asymptote. If I put it at -3, you'll notice that the graph does approach that line but never touch it. So now what we want to do is use limit notation to describe what the graph is doing as you approach this -3 value. So here's how you're going to have to do that. So you're going to have to look at the limit as the x values approach, and then here we're going to approach what? -3 from the left, or from -infinity. So as I approach -3 from the left, so that's what all this notation means. X approaching -3 from the negative side or from the left. As I approach -3 from the left, what are the y values doing? Well, look at the graph. What's it doing? It's going down. So the y values are going towards -infinity as I approach -3 from the left. So that's what's happening on the left. Now I need to look at the graph, or the y values, as I approach -3 from the right. Okay, so this is how we use limit notation. So we use positive sign to approach from the right. So starting over here on the positive side, and as I look at, or as I approach -3 from the positive side, what are the y values doing? Well, they're going up to positive infinity, so the y values are going towards positive infinity. So this is how you use limit notation to describe the vertical asymptote. And then as we looked at in that definition box in the previous slide, if you're going towards an infinity from both sides, which we are, from the left it's going towards negative, from the right we're going to positive, then that means that the line x equals -3 is indeed a vertical asymptote. Okay, so that's how you use limit notation to describe vertical asymptote, and then that's why it is an asymptote, is because the limit is approaching an infinity from both sides. So let me go ahead and do this second example for you. So again, we want to look at what creates zeros in the denominator. So again, it's not in factored form, but I have to figure it out for myself. I notice that this is the difference of two squares, so I can factor this into x plus 2 times x minus 2, and now I can figure out the zeros, -2 and 2. So that means I should have vertical asymptotes at the line x equals 2 and the line x equals -2. So if I graph this on my calculator, that's indeed what I get. I have a vertical asymptote at -2 if I place it right here, and I have a vertical asymptote at +2. So I indeed have asymptotes at these two places. So now I want to use limit notation, and I have to use limit notation to describe each one separately. So I have to approach -2 from the left and the right, and I have to approach +2 from the left and the right to write the limit notation. So the limit as x approaches -2 from the left is, so -2 coming from the left, the y values are going down towards -infinity. And then the limit as I approach -2 from the right. Okay, so as I go towards -2 from the right, the y values are going up towards positive infinity. So this is limit notation describing the asymptote at -2, x equals -2. Now I have to use limit notation to describe the asymptote, the vertical asymptote at +2. So I do the same thing. I have to look at the x values approaching 2 from the left. Okay, so as I come towards +2 from the left, the y values are going up towards positive infinity. And then I need to look at the x values as I come towards 2 from the right. So as I come from 2 from the right, the y values are going down towards -infinity. So these two down here describe the vertical asymptote at x equals 2. These two describe the vertical asymptote at x equals -2. All right. So this is using limit notation to describe vertical asymptotes. I'm going to do this one last example if you'd like to continue to watch. If you think you got it, then you can stop the video and go ahead and tackle your homework, but I will do this last one for you. In this last example, again, we look at the denominator. It's not in factored form, so I have to determine the zeros for myself. Again, I recognize this as the difference of two squares, so I can factor it. So -1 and +1 are where my asymptotes are going to occur. So again, if I graph this, I can see that I do have a vertical asymptote at -1 if I put that there, and again at +1. So now I'm going to use limit notation to describe both of those asymptotes. So I need to look at the limit as x approaches -1 from the left. So as I come towards -1 from the left, the y values are going up towards +infinity. And as I approach these -1 from the right, so as I come towards -1 from the right, you'll notice these go down towards -infinity. So this describes the vertical asymptote at x equals -1. So now I'll use it and describe as I approach from x equals +1, what about that asymptote? So the limit as x approaches 1 from the left, so as I come towards +1 from the left, you'll notice these y values are going down towards -infinity. And as I approach the +1 from the right, as I come from the right, you'll notice the y values are going up towards +infinity. So this would be limit notation describing the vertical asymptote at x equals 1. So a couple things to remember from this lesson, or what I need you to remember from this lesson, is that a rational function is a polynomial over another polynomial. Number 2, the zeros of the denominator are where the vertical asymptotes are created. And number 3, know how to describe the vertical asymptote using limit notation. Okay, approach it from the left and approach it from the right, and both of these should be approaching an infinity, whether both positive infinity, both negative, or one positive, one negative, doesn't matter, as long as they should both be approaching an infinity for it to correctly describe a vertical asymptote.